Yes, how are you, my students? Welcome to lecture 4. We are going to look at atomic masses, formula, and solutions formed by compounds. So that one is going to mark our lecture 4. So now, first of all, we want to look at atomic rules. Remember back in high school in Form 2, you learned something about the atomic structure. Then you say that an atom is the smallest particle of an element which participates in a chemical reaction. So an atom itself has what we call subatomic particles. Among the subatomic particles, you mentioned something about electrons, you mentioned something about protons, and you mentioned something about neutrons, where we said protons and neutrons are normally concentrated at the center of an atom, while electrons normally occupy a large region surrounding the nucleus. So now, there are some terminologies we are going to define as we look at the atomic rules. So one, we say that the number of protons in the nucleus of an atom is equal to the atomic number, which is normally given letter Z. Then in a neutral atom, the number of electrons is equal to the number of protons. I believe that one, you have some knowledge about it. In any given neutral atom, the number of protons must be equivalent to the number of electrons. And that's why a neutral atom doesn't usually have a charge. Then what about mass number? Mass number of an atom is equal to the sum of the number of protons and the neutrons in the nucleus. So if you want to get the mass number, you must take the number of protons in a given atom plus the number of neutrons contained in a given atom. So that one will give us the mass number. So remember, the number of neutrons is equal to the difference between the mass number and the atomic number. So once you have developed that relationship where mass number is equals to protons plus neutrons, in any circumstances, if you are given mass number and number of protons and they want you to get the number of neutrons, it means you take mass number minus the number of protons. In the same way, if you are given neutrons and mass number and they want you to work out for the number of protons, you take mass number minus the number of neutrons. So now we have a question here. It asks how many protons, electrons, and neutrons are in an atom of, this one is potassium. So potassium is normally given letter K. So 40 represents the mass number. Then 19 represents the atomic number. So atomic number is equivalent to the number of protons. So once you know the number of protons and you have the mass number, I believe you can be able to get the number of neutrons. And remember, the number of protons is usually equivalent to the number of electrons in any given neutral atom. So I think with that one in mind, basically here, if you take 40 minus 19, you will get 21. It means potassium has 21 neutrons. But when it comes to protons, protons is the same as the atomic number. So this element has 19 protons. Then protons are equivalent to electrons. So that means K has also 19 electrons. So now we proceed and look at relative atomic mass. Again, we were able to define this terminology in Form 2, where we said relative atomic mass is the average mass of atoms of an element relative to the mass of an atom of carbon-12, which is arbitrarily given a value of 12.00 atomic mass unit. So remember, there were so many theories which were formulated when we were trying to work out relative atomic masses of different elements. So they were working on it to see which scale is the best to determine relative atomic masses of different atoms. And remember, they settled on carbon-12. That's why we compare the atomic masses of different elements in relation to the mass of carbon-12, which is given that value. So now we want to look at isotopes. So what are isotopes? So you discover that isotopes are atoms of the same element with the same atomic number but different mass numbers, or we talk about different number of neutrons. In chemistry, you have various elements which normally exhibit isotopes, but we have other elements which doesn't have isotopes. So now we want to look at some of the elements which exhibit isotopes. For example, carbon. Carbon has this symbol as C. So 12 is the mass number of carbon. Then the atomic number is 6. So if you want to get the number of neutrons, you can see you take atomic number. Then you get a atomic number, and then you subtract from a mass number. So they have used this kind of relationship there. So these are isotopes of carbon. You can see you have 1, 2, 3, 4. So they have the same or equivalent atomic number, but the mass numbers varies. You can see we have 11, 12, 13, and 14. So the same thing is observed with hydrogen. Hydrogen has 3 isotopes, as you can see in this table. So from that table, you can see that so the first isotope has atomic number of 1, the second one atomic number of 1, then the last one atomic number. But the mass numbers, you have 1, 2, and 3. So these are the names of these isotopes. This one is hydrogen, deuterium, and tritium. It refers to that hydrogen with a mass number of 3. So these are atomic mass units. So 1, 2, 3. These are natural abundance. So remember, each normally contributes a certain percentage of atoms to the total atom of that particular hydrogen. So this first one will contribute 99.985 atoms. Then the second one contributes 0.015 atoms. The last one contributes they talk about trace. That means it contributes a negligible percentage. A negligible percentage to the total mass. That means when you take this one plus that, it basically gives you 100%, because the sum must be 100%. So that means this last one, its contribution is actually negligible. So now that one of magnesium, it has 3 isotopes. The first magnesium, the mass number is 24. The second isotope, the mass number is 25. And the last isotope, the mass number is 26. So these are atomic mass units. Then these are the contribution of the respective isotopes to the total mass. So if you are given this kind of information and they want you to work out the atomic weight of a given element like magnesium, so you normally apply the formula atomic mass, relative atomic mass or atomic weight is equals to, you take the mass of the first isotope times its relative abundance plus mass of the second isotope times its relative abundance plus mass of isotope 3 times its percentage abundance. Then we divide by the total percentage or abundance. So the total abundance must always be 100. So that means the first isotope, its mass is 24. So remember here they have given us the exact values. So it is 24. They have used 23.98 times percentage abundance, which is 98.99 plus the second one, the mass is 25, but the actual one is 24.985837 times percentage abundance is 10 in brackets, and then plus the mass of the third isotope is 26. So the actual value is 25.982593 times 11.01 divided by the total percentage abundance. That means you add all these percentage abundances. then you divide. So if you work out accurately, you will settle to this value. So atomic weight of magnesium is 24.305. So basically that is how you can work out the relative atomic mass of any given isotope. So we want to proceed and perhaps look at other examples. And before I proceed, remember the relative atomic mass of any given isotope is always close to the mass number of that isotope, which is always of the highest percentage abundance. And in this case, it is this first isotope. You can see the abundance is 78.99%, which is almost 79%. So its mass is 24. So when you look at the relative atomic mass, 24.305 is close to the mass of that first isotope. So now you can apply that formula generally to work out if an isotope has maybe two isotopes, an atom has two isotopes, it can have 3, 4, and 5 like that. So you apply the same formula to work out the relative atomic mass. So this example 1, they have given us an example of boron. So boron has two naturally occurring isotopes. In a sample of boron, 20% of the atoms are B-10. So it means the first isotope has a mass number of 10 and the percentage abundance is 20. So the other 80% of the atoms are B11. So it means this 11 is the mass number of the second isotope. Then percentage abundance is 80%. So they want you to work out the atomic mass of boron. So that means boron has two isotopes. So we apply that a formula there. Percentage of isotope 1 times mass of isotope 1 plus percentage of isotope 2 plus times mass number of isotope 2. Then we write all percentages as decimals. So that means 80%, it will be 0.8. 20% is the same as 20 all over 100, which will give us 0.2. So from this working, you can see isotope 1, you take 1%, which is the same as 0. Isotope 1, its percentage abundance, you take a 20 all over 100, which will give us 0.2, but the mass is 10. The second isotope, its percentage is 80 all over 100, which is the same as 0.80. So mass number is 11. So to get the atomic mass, you take 0.20 times 10 plus 0.80 times 11, which will eventually give us 10.8 atomic mass unit. So this one is the same as when you just take 20 times 10 in brackets plus 80 times 11 in brackets, then divide by 100. It will arrive at the same answer, which is 10.8. So that means the average mass of boron atom is 10.8 atomic mass unit, and this one becomes our relative atomic mass of boron. So they have given us the second example, where they have given us this element neon. It has these isotopes. The first one has the percentage abundance of 90.92%. The mass is 20. The second one has the percentage abundance of 0.3, and you can see the mass is 21. So they want you to work out the relative atomic mass of neon. So this is how it has been worked out. There are 3 isotopes. So the first one, the percentage abundance is 0.9092. Second isotope is 0.003. The mass is 20.99. The last one is 0.0885. The mass number is 21.99. So you can just go about the question and be able to see. So now that is the information. So the values has been given respectively. You can see the first one, percentage abundance, mass number. The second one, percentage abundance, mass number. Then the last one, percentage abundance, then mass number is given there. So that means now when it comes to calculation, you take 0.9092 times 19.99 plus 0.003 times 20.99 plus 0.0885 times 21.99. So remember already those percentages have been converted to decimals. So that's why there is no need to divide by 100, because we have converted the percentages in terms of decimals. So once you just multiply, you get the sum, which will eventually give us the relative atomic mass, which is 20.17 atomic mass unit. So that means the mass of an average neon atom is 20.17 atomic mass unit. So you can have a look at it. So now we have self-test questions which you are supposed to attempt. The first question you can see have been given there. They're talking about isotopes of element X. So the first isotope has the mass number of 10. Percentage abundance is 81.8. Then the second isotope, the mass number is 11. Percentage abundance is 18.2. So you are supposed to calculate the apparent atomic mass of this naturally occurring sample of X. So that means you'll take 10 times 81.8 in brackets, 11 times 18.2 in brackets, divided by 100. Because if you take 81.8 plus 18.2, you will get 100%. So you divide by 100. So with that in mind, you can work out the second example, question 2 and question 3. So now question 4, they are saying an element X has two isotopes, X minus 6. So 6 is simply representing the mass number of the first isotope, which is X. Then 7, mass number of the second isotope. So they are saying if the relative atomic mass of X is 6.94, determine the percentage abundance of each isotope. So in that case, you have not been given percentage abundance for any isotope. But remember, from chemistry, the total percentage abundance must always be 100%. So each of the respective atom will contribute a certain portion to the total mass. So that means we now follow this particular working. So I hope it can be seen clearly. This one, we say let the total percentage abundance be 100. So that now we say isotope 1, which is X minus 6, let its percentage abundance be X%. So if this one is X%, it means the second isotope, you take 100 minus X, which is 100 minus X%. So therefore, relative atomic mass of X is equal to mass of the first isotope times its relative abundance plus mass of the second isotope times its relative abundance divided by 100. But we know relative atomic mass of X has been given in the question. It is 6.94, which is equivalent to 6 times X plus 7 in brackets 100 minus X all over 100. So when you work out, the value of X will be 6. So I hope you can see the value of X is 6. So it means now this X here is 6. So to get the second percentage abundance for this second isotope, you take 100 minus X, which is 6. So down there you can see. So now we take the second isotope, we take 100 minus 6, which will give us 94%. So I hope it is very clear. You can see how it has been worked out. So from the start, the working is very, very clear. You can have a look at it so that you can analyze. So then next we look at chemical formula, that's molecular and ionic substances. So remember, various compounds are normally represented by use of chemical formula. So use the chemical symbols to represent you give a representation of a given compound to show how various atoms combine in different proportions in a given substance. So chemical formula of a substance is a notation using atomic symbols with subscripts to convey the relative proportions of atoms of the different elements in a substance. So I think you are in chemistry, you have been able to look at various chemical substances. So these are examples of molecular substances. You can see molecular formula of water from high school chemistry. It is H2O. Then ammonia, NH3. Ethanol is C2H6O. So you can see they are showing the ratios in which those atoms combine to form a compound. For example, in ammonia, we have one nitrogen atom combining with 3 atoms of hydrogen to form one molecule of ammonia. So these are open structural formula. They are showing the bondings. Then these are the models, 3-dimensional representation of those molecules. Then these ones are a molecular model, space filling type. Such actually describing the same molecular substance. So you can have a look at those particular molecules. So now we have some terminologies that we want to define. What is a molecule? A molecule is defined as a group of atoms that are chemically bonded together, tightly connected by attractive forces. So it's a group of atoms which are chemically bonded together, tightly connected by attractive forces. Then a molecular substance is a substance that is composed of molecules, all of which are alike. So they must be alike. They must be identical. So when they combine several of them, they form molecular substance. Like in sugar, when you look at sugar crystals, sugar falls under molecular substance. So it's normally made up of sugar crystals. And those sugar crystals are actually in form of molecules. Then a molecular formula gives the exact number of atoms of elements in a molecule. So like the previous, these molecules that we have just looked up here. So you can see like in ethanol, ethanol is a molecule. It has 2 carbons combined with 6 atoms of hydrogen and 1 atom of oxygen to form a molecule of ethanol. So that means a molecular formula gives the exact number of atoms of elements in a given molecule. So structural formulas show how the atoms are bonded to form to one another in a molecule. And I think you have been able to look at the structures of, you can see now like in water, you can see that's a formula showing how those atoms are actually bonded in that particular molecule. And even ammonia, you can see 3 hydrogen atoms joined to that central nitrogen atom. Then we move forward and look at ionic substances. What are ionic substances? So these are substances which are composed of ions. For example, sodium chloride is an example of an ionic substance. And we said in sodium chloride, sodium ions are normally positively charged, while chloride ions are negatively charged. Those ions usually originate from atoms which either loses electrons or gains electrons, like sodium atom loses electrons to form positively charged ions of sodium, while chlorine atoms gain electrons to form negatively charged particles of chloride ions. So when they attract each other, they form an ionic compound. So an ion is an electrically charged particle obtained from an atom or chemically bonded group of atoms by adding or removing electrons. And they have given us sodium chloride as an example of anionic compound. So now we look at the formation of ammonia. How is ammonia formed? Remember, ammonia is formed by the reaction of nitrogen gas and hydrogen gas. So one molecule of nitrogen combines with 3 molecules of hydrogen gas to form 2 molecules of ammonia gas. So this one is just a representation. It means we have 2 atoms of nitrogen plus 6 atoms of hydrogen to give us 2 atoms of nitrogen and 6 atoms of hydrogen. So if you work out the total number, so these 2 atoms of nitrogen forms 1 molecule of nitrogen, 6 atoms of hydrogen forms 3 molecules of hydrogen to form 2 molecules of ammonia. So that means we have, if you have, in case now, applying that ratio, if you have 10 molecules of nitrogen, we shall require 30 molecules of hydrogen to form 20 molecules of ammonia. So here you apply actually the mole ratio of the respective reactants and the product. Now, in terms of Avogadro's constant, it means this one, remember, this is 1 mole of nitrogen gas. So it contains this number of molecules of nitrogen gas in terms of Avogadro's constant. So you take 1, which is 1 mole of nitrogen, times Avogadro's constant, which is normally 6.02 times 10 to the power 23. But now it becomes in terms of molecules. Then this one you have 3 molecules, so you take 3 times Avogadro's constant. Here you have 2 moles, so you take 2 times Avogadro's constant. It will give us this number of molecules in that ammonia. Then in terms of the moles of molecules, this one is 1 mole of nitrogen molecule, 3 moles and 2 moles. In terms of mass now, remember 1 nitrogen has a relative atomic mass of 14, but we have 2 atoms here, so you take 2 times 14, which will give us 28. 1 hydrogen has a mass of 1 gram, and they are actually 3, so you take 3 times 2, which will give us 6 grams. This one will be 6 grams. Remember, every atom has a mass of 1 gram, and there are 3 times 2, we get 6 atoms. So 6 times 1, it will give us 6 grams. Then this one molecule of ammonia has a mass of 17 grams, and there are 2 molecules of ammonia, so we multiply 2 by 17 to get 34. So this one is 34 grams. So here they have taken 28 plus 6 to give us 34 grams. Then in terms of molar gas volume, so 1 mole of a gas can occupy 22.4 liters at STP. And this one is 1 mole of a gas. These are 3 moles, so you take 3 times 22.4. So it is 22.4 plus 22.4 plus 22.4 to give us 67.2 liters. Then here we have 2 moles of ammonia gas, so you take 2 times 22.4, which will give us 44.8 liters. So you can have a look at that table. So next I will look at stoichiometry. Remember, in form 3, under mole concept, you are able to learn something about stoichiometry, where the mole ratio of reactants and products are usually represented by use of whole number ratios. So in this case, that mole ratio is normally indicated by the coefficients in a balanced equation. Like in this case, magnesium combines with oxygen to form magnesium oxide. So the coefficient of magnesium is 2, the coefficient of oxygen is 1, and the coefficient of magnesium oxide is 2. So that means the mole ratios for reactants is 2, then here it's 1, then on the product side, this one is 2. Then we proceed and look at the formula weight. What is the formula weight? This is the sum of the atomic weights for the atoms in a chemical formula, just as the same way as a relative atomic mass. So it means to get the formula weight, you take the sum of the respective relative atomic masses of the atoms in a given compound. So since we are talking about weights, we talk about now atomic weights. You get the sum of the atomic weights. Like in magnesium oxide, we know that 1 mass of magnesium usually has a mass. It's normally given a mass of 24. So you take 24 plus oxygen is 16. It will give us the mass of magnesium oxide. So the same thing has been explained here. Look at calcium chloride. One atom of calcium has a mass of 40. One atom of chlorine has a mass of 35.5 from chemistry. So if you want to get the formula weight of calcium chloride, we take the mass of calcium, which is 40.1, plus the mass of 2 atoms of calcium. So two atoms of chlorine, I mean. So it means we take 40 times 1 plus 2 times 35.5, which will eventually give us 111.1. That one marks the atomic mass unit of calcium chloride. So these are generally reported for ionic compounds. So when you talk about ionic compounds, we get their formula weight. They talk about relative formula mass in that case. Then molecular weight. This one is normally applicable to substances which are in the form of molecules. So in the same way, molecular weight is the sum of the atomic weights of the atoms in a molecule. Like ethane, we can't say that ethane is an ionic compound. No, ethane is a molecule. You can see it has 2 atoms of carbon and 6 atoms of hydrogen. So how do we get the molecular weight? So the molecular weight now can be found by taking the mass of 2 atoms of carbon. One atom has a mass of 12.0. So we take 2 times 12.0, then plus 6 times 1. So the atomic mass of one hydrogen atom is normally 1 atomic mass unit. So once you get the product of the two, then you add, it will give us 30.0 atomic mass unit. So this one becomes the molecular weight of ethane, because this one is a molecule. So if the chemical formula is merely an atom, formula weight is equal to the atomic weight. For example, if you are given the carbon as an element and they want you to work out the formula weight, so the formula weight in that case will be the same as the atomic mass of carbon, which is 12. The atom of carbon has a mass of 12, so that is the formula weight of carbon. It's just the same. So the formula weight is the same as the relative atomic mass of a given element. If it is sodium, it's normally 23. So the relative atomic mass of sodium is the same as its molar mass, which is 23. So if the chemical formula is merely a molecular compound, then formula weight is equal to molecular weight. So like in this case, its molecular weight is the same as the formula weight of this substance. Only that this one is a molecule, that's why we use a different term, molecular weight. But if it was a compound like sodium sulfate,